that A and B were coprime. Okay, so today I'm going to do, it's going to be a little bit of a technical day, okay? So today we're going to do more induction. So all right. And so we've been talking about two types of induction. So about two types. Induction, so we had this usual induction, right? So we had the usual, or weak, what we'll call today weak induction. Logicians just call this induction. I guess they just call both just induction. Okay, so weak induction says that if you have P of 1 and you have that for every natural number, P of n implies P of n plus 1. So if you have these two statements, then these imply for all n in the natural numbers P of n. Okay, so this implies this, okay, this statement here. So this was the base case, and this is the inductive hypothesis. Okay, so this is, okay? So P is just a predicate with a free variable over the natural numbers. All right. Okay, and then we had a strong induction. Okay, and strong induction says that if you have P of 1 and you have a strong inductive hypothesis for all n in the natural numbers, so we have, or we'll do it like this. We'll do it like this. 1 less than or equal to k less than or equal to n. Pk, this implies p n plus 1. Okay, so this is this strong inductive hypothesis. Okay, these two statements here imply for all n in the natural numbers, P of n. Okay, so this is the base case. You have a strong inductive hypothesis here. Here you have a base case. You have just the usual inductive hypothesis. In both of them, the conclusion is P of n for every n in the natural numbers. Okay, so the question is, okay, so recall that for in our axioms, or axioms for the real numbers, or sorry, for the natural numbers, for n, we included this like an axiom for induction. Okay, so the usual induction. Okay. Okay, and so the question you can ask is, so are these two versions, the two versions of induction logically equivalent? Because it seems like the strong induction one, you get to assume more, right? And so the weak induction one, you can assume less. So the spoiler answer, so the answer is yes. Well, if you modify your axioms a little bit. Modify the axioms of the natural numbers slightly. Okay, and this is to, so let me just say the fancy words and then I'll say what it means. So in what's called piano arithmetic. Okay, so we initially gave 5 axioms, right? They were mostly about the successor function. But in what follows, right, okay, we gave 5 axioms, right? 4 of them were just involving the successor function, like 1's the beginning number. Every number has a successor. If you have 2 numbers and the successors are the same, then the 2 numbers are the same. Okay, so you had some axioms like this, and then you had this axiom of induction, right? And so conceivably, you could ask if you could replace that axiom of induction with an axiom of weak induction. Okay, well, okay, as it turns out that these, if you can't just do that in the normal axioms that we gave, we have to add a little bit more. Okay, and the little bit more has to do with this inequality sign. Okay, so let me just make a claim here. Okay, and I'm going to just do the claim, and I think it'll become clear, and then I'll talk about what I used and how I have to modify the axiom slightly. Okay, so let me say a theorem. So weak induction and strong induction are logically equivalent. So i.e., given, if I am allowed to assume that a weak induction holds for every proposition, I can deduce a principle of strong induction. Conversely, if I assume a principle of strong induction, I can assume I can derive the weak induction axiom. Okay, and so before going on, let me say a little bit about. Let me give you some notations, right? So there's some notations I may or may not use, or you might see other places. So a proposition P, let's say R, about the natural numbers, let's say Rn, with a free variable in the naturals, the following are the same. Okay, so if I do something like this, Rj, okay, so this is the same thing as here, for all j less than or equal to n, Rj. So I could quantify like this, or this is the same thing as for all n in the natural numbers, let's say for all j in the natural numbers, j is less than or equal to n implies Rj. Okay, so here, so this is one way of, there are different ways of writing the same thing. This one's a little bit more clear here that we need a new symbol when we look at this thing. So in the original axioms that we gave, the Dedekind-Peano axioms, there was no way to talk about less than or equal to for 2 natural numbers. Okay? And so I'm just going to be using the less than or equal to and some obvious properties of less than or equal to in order to derive this equivalence. Okay? Okay, and I might say a little bit more about that. Okay. So what I did in the other class is I just went through the proof without really saying anything, and I think it doesn't really hurt to do that either. So I think it becomes kind of clear that what this thing should do. Okay, so so let's do the proof. Okay, so let's do the proof. Okay, so suppose the principle of weak induction holds in our system. Okay, so this means for every proposition R, R of n, okay, we have the following. So this is some predicate. So this is a predicate for the natural numbers. So we assume that R of 0 and this inductive hypothesis, so this is the base case. So if we have the base case, and we have that for every natural number, R of n implies R of n plus 1. So if we have these two things, then we get to conclude, so this is this other axiom here, we get to conclude that for every natural number, R of n is true. Okay? So we want to conclude now that there's some, so we want to conclude a strong induction method works. Okay, so what we'll do is, to do this, so here we let P of n, so let P of n be a proposition or a formula with a free variable n. Okay, and I'm going to do induction on this. I'm going to show the strong induction formula holds for this guy. So the strong induction is that when I assume a stronger inductive hypothesis for this guy, right, then we're going to be able to conclude for all n P of n. Okay, so and we'll define here Q of n to be this thing. Okay, so P of n. Okay, so note that this is the thing, the thing that appears in the inductive hypothesis for strong induction. Okay, so this is what we have. Okay, and so I defined this thing. It's fair game. So since induction holds, weak induction holds, we have the following. Okay, and now I'm just going to write the formula for weak induction. So the axiom of weak induction with this Q of n. Right? It says Q of 0 and for all n in the natural numbers, Q of n implies Q of n plus 1. Okay, so this is the base case. If we have the base case and we have the inductive hypothesis, right? Since we're assuming that a version of weak induction holds, then we get to assume that for all n in the natural numbers, Q of n. Okay, so this is what we have. So I claim that this formula here is really, when we write it out with Q's like this, that it's really the usual, so that this is strong induction. Okay, so the claim, so I claim this formula is really the strong induction principle. Induction for P of n. Okay, so I claim that this is really the strong induction for P of n. Okay, so there's two parts that are kind of easy here. Oh, sorry. I've been doing this. This is Q of 1. So, so R of 0 as well. OK, so I have a habit of doing the natural numbers with 0. OK, so if I write zeros, you guys stop me and tell me I should write a 1. OK, but is anyone confused about why I replace it with 0 instead of a 1? So I'm starting with 1 instead of 0. Cool. Yeah. So in the natural numbers, right, the natural numbers have a starting point, right? And we can either choose that starting point to be 0 or the starting point to be 1, right? And so when you want to prove something by induction, you have a base case, which would either be R of 0 or R of 1, right? And since today I started with R of 1, I should be consistent and start the inductive thing, the induction at 1 instead of 0. It doesn't really matter so much, right? There's two flavors of this whole thing. You could start it with 1s or you could start it with 0s, and it doesn't really matter, right? I just had the habit of writing 0s, but so you'll see me write. You may catch me again writing a 0 instead of a 1, but it shouldn't really matter. Just remind me, and I'll switch it. Okay? Okay. Okay. So so this. Do you guys see that this thing holds here? Okay. So let's go back to what we're doing. We're assuming weak induction. I defined a formula like this. And I want to show that this thing is really the strong induction formula, okay, for P, which means that we assume this and we get to conclude P of n plus 1. Does that make sense? Okay. So so here are the two obvious parts. So the obvious parts. Okay. The obvious parts are that Q1 is really P1. These two things are logically equivalent. So if I take the and if I just have one of these things, we just have the base case. The two base cases are the same. The other obvious part is that if for all n in the natural numbers, if I have Q of n, right, this is the same thing as for all n in the natural numbers, P of n. Okay, so here, well, let's try and write them the same, I guess. Okay, so here we're just doing a big conjunction of P1, P2, P3, but there might be some repetition. Okay, so Q2, for example, has P1 and P2. Q3 has P1 and P2 and P3. But this is really just a big and, as we talked about for quantifiers. And then here, this is just P1 and P2 and P3 and P4, so on and so forth. So do you guys see that these two things are logically equivalent? Okay. So those are the obvious parts. So we really have taken care of this, and we've taken care of this. So my claim now, it remains to show that this part here, so it remains to show that this statement here, for all n in the natural numbers, here that Qn implies Qn plus 1, is logically equivalent to the strong inductive hypothesis. Equivalent to the strong inductive hypothesis. Inductive hypothesis for P, i.e., this is for all n in the natural numbers. If this thing holds, n Pj implies P of n plus 1. Okay, so this is what we want to show, that this thing and this thing are the same. Yeah? So sorry, what's the relationship between R of n and P of n?
Why don't you have to,
I mean, I could have said R. So okay, so technically, so I could have said R of n is P of n, but really there's a quantifier here, so it's saying for every R of n, right? And then I'm fixing a particular P of n. And I'm wanting to show that that's true. So it's like I'm getting rid of a quantifier, really. But I could have called this R. I could have called P R. It doesn't really matter. It's your choice. Right? Okay. Okay. So so here's my claim. Okay. Here's the claim that'll fix this. The claim. So A implies B. This thing's equivalent to A implies A and B. Okay, so there's the claim that I want to show. Okay, so this is just for propositional logic. Okay, so these are just propositions. Okay, but let's suppose the claim for a second. Suppose that I know this. And let me give you kind of an intuitive explanation of this. Okay, so this one is just A implies B. If A, then B. This is saying if A, then A and B. So really, you already have one of the conclusions already in here, right? So I'm saying that this doesn't really hurt to say that, okay, we're implying the conclusion as well. Does that make sense? Okay, that's the idea. Okay, so let's suppose that we're given the claim for a second. The claim, right? So we want to relate this one to this one. This one to this one here. Right? We want to relate these two things here. So with A being so A will be Q of n, and B being P of n, right? We will be done. Right? So here, so let's in this one, so note that Q of n plus 1 is really this thing. Less than or equal to n plus 1 of Q of n, or Q of k. And so this is really this thing, 1 less than or equal to, P. This is 1 less than or equal to k less than or equal to n. And this is really P of k and P of k plus 1, or P of n plus 1. Right? So this thing, this is really, B should be P of n plus 1. Okay? So this is really, this part here is really Q of n and P of n plus 1. Okay? So what this is really saying is that the claim is we have this thing, Q of n implies Q of n plus 1. So Q of n implies Q of n plus 1. So this is really Q of n implies Q of n and P of n plus 1, right? And this is by the claim. This is really Q of n implies P of n plus 1. Okay? So we have A and B, and this is A and this is B. Okay? So that those two things are the same. Okay? And this thing here, A, this is the strong inductive hypothesis. Okay? So this is like the usual inductive hypothesis, right? The weak inductive hypothesis. And then when we write it out, it breaks up into the strong inductive hypothesis. Does that make sense? Okay, so so given the claim, we show that this thing is really, we really get strong induction. Okay, so this guy here is really the strong inductive set. So given the claim, let me just say that again. We have that this thing Okay, so we have this. So this is the thing that we got from using the weak induction, and then this is the strong inductive hypothesis. So, and we know the conclusion because we had that big formula written down that this thing and this thing, we wrote down the formula for weak induction with Q, okay, and that was given. Okay, so let me prove the claim. Okay, so the proof of the claim. Okay, and the proof of the claim just follows from using the definition of implication. The definition of implication. Okay, so we'll start from the right-hand side and we'll go to the left-hand side. So A implies A and B. Okay, so how did we define implication? So we defined it to be not this guy and not the conclusion. Remember, it was not the hypothesis and not the conclusion. Right? So that would be the contradiction of an implication. So we defined it to be this thing. So it's not A and not the thing that follows. Okay. So let's use our De Morgan's law. So this is not A or not A and B. Okay? So this thing is the same thing as not A or A and B. And now we use the distributive law. So this is equivalent to not A, and now I distribute it, or A and not A or B. Okay? So this is true and something, right? So this is not A or A. So this is true and something else, which was this thing, not A or B. Okay? And so that thing here, so when you do true and you do and of something, that's just the original thing that we have. Okay? So this is equal to not A or B. Okay? And this is the same thing as A implies B. Okay? So we showed, this proves that these two things, that this is logically equivalent to this. Yeah?
For any implication, can you say, if you're saying A implies B, can you say A implies A and B?
Yeah.
Okay.
Yeah. So, yeah. So you can always, it's always like assuming that your hypothesis was also true in the conclusion. So yeah, you can do that. And that's what this shows. Yeah. Okay, so this shows, so we've shown that weak induction gives a strong induction. Okay, so weak induction, if we have a weak induction principle, we can derive a strong induction principle. Okay, so now let's go the other way. Let's do the other direction now. Other direction. Okay, so suppose a principle of strong induction holds and conclude a weak induction. Holds. Okay? So what does this mean? So strong induction means, means the following. Means for every predicate R of n, a predicate with a free variable in the natural numbers, so this is something that's true or false depending on which natural number we do, we have the following. R of 1, and now we do our strong inductive hypothesis. So for all n in the natural numbers, that this big conjunction, R of j, when j is less than n and 1, that this implies R of n plus 1. Okay, so we have this. So this is the base case in the strong inductive, so this is the strong inductive step, and this is the strong inductive hypothesis. So using the strong inductive hypothesis for the numbers less than or equal to n, we get them for n plus 1. Then this implies that for all n in the natural numbers, R of n holds. Okay, so we have this big statement here, right? And the conclusion is this statement here, that for all n in the natural numbers, R of n holds. Okay? So now I guess I'll stick with R of n here. So I could have done p's, but I'll do it like the other way now. Okay? So for this one, okay, so now we want to show a weak induction principle holds. So the easy parts, again, show the weak induction for R of n. Okay, and so intuitively, here we're really supposing something really strong, right? So what we want to do is we want to suppose. So what we'll do is we'll suppose. Okay. So let me start with blah. Okay. So we want to show that if this were a weaker hypothesis, that we'd have a similar statement. So if I just assumed R of n instead of this big conjunction here, then we would get something. Okay. So okay. So the trick here / claim is the following. So if A implies B, then A and C imply B. So this is the idea here. So this is what's called an and introduction into the hypothesis. So here, so notice that if this thing is true, so the idea, well, let me just say it verbally, okay? So here, right, here if we assume the stronger, so we are given this, right? But here if we are given a stronger assumption, right, then we also can conclude B, okay? So in order for this to be true, both A and C have to be true. In particular, A is true, so B is true. Does that make sense? So if we have this statement, then we get this statement. We can impose additional hypotheses. Okay? So in our application, right? So we have this weak inductive hypothesis. The weak inductive hypothesis is the following. The statement is that for all n, well, I'll write it without the quantifiers. R of n implies R of n plus 1. Okay? And then we have the strong inductive hypothesis. Okay? So for all say j less than or equal to n less than or equal to 1, R of n implies R of n plus 1. So here, so the way we're doing it, so A is R of n in the application. A is R of n. B is R of n plus 1. And C is this big conjunction, J less than n of R of j. Okay, so here, okay, so here, let me just take a sip of water real quick. Okay, so where was I? Okay, so we're trying to show, okay, so where were we again? Okay, so we're trying to show that strong induction implies a weak induction hypothesis, right? So whenever we have this situation, right, so for every proposition we have this situation. So for every R, if we have this R1, the base case, and the strong inductive hypothesis, we can conclude this. Okay, what we need to show is that if we're given the base case and a weak inductive hypothesis, then we can conclude the conclusion, right? Yeah?
Why is that just like j is less than n, not less than n?
Yeah, because what we're doing here is I want, so this is going to be the strong inductive hypothesis, right? And this is the weak one. And my statement is that the strong inductive hypothesis is really the weak inductive hypothesis plus all the other lower cases, right? And so, yeah, these are all the other lower cases here. Does that make sense? Okay, so this means, okay, this means if we are given, R1 and the weak inductive hypothesis, and for all n in the natural numbers, R of n implies R of n plus 1, right? We can conclude we get the stronger statements R of 1, so that's not really stronger, but we do get this one, where we introduce more things. Here. Okay, and since the principle of strong induction holds, we get to conclude that for all n, R of n. Okay, because if we had that weak induction, so if we're given the weak induction hypothesis, right, that this thing with this weak sauce hypothesis, right, well, we might as well just throw in the extra hypotheses because we showed that if we're given one, we can get the other, right? Okay, since we get that and we have this, we get to apply the principle of strong induction to get this one. Does that make sense? Okay, so it's the idea was, yeah. So this one was we introduced. So strong induction is really introducing an extra hypothesis, but the point is that strong induction assumes more, right? So yeah. So it should be easier to prove things. Okay. Let me see where we are with time. Okay. So are there any questions on this? Okay. So in the next class, I'll say a little bit about, okay, so I cheated, okay? I told you that I was going to cheat, and I did cheat somewhere. The cheat, so the last remark about this is that, so how did I cheat? Okay. We cheat. Okay? So in our formulas, we use the symbol less than or equal to. Okay? The less than or equal to really came from these conjunctions here, and which isn't available to us in this Dedekind-Peano okay, we are only allowed to use things that we're only allowed to talk about things that are given to us. All right. What's in technically, I've said this once before, but there's a thing called a signature. Okay, and so that's essentially all the symbols that you're allowed to use. Okay, and so to make the proof, the strong induction, weak induction proof rigorous, we need to say, we really need to introduce some extra axioms that allow us, for the natural numbers, that allow us to talk about inequalities. Okay? So we'll talk about this next time. So with the remainder of time, why don't we do some more induction handouts? So exercises. Let's do the handout axioms. So that the handout 3, handout 3, the one on induction. And I want you guys to try, I think it's the one about the Fibonacci numbers. 19. Okay, so let's do this one.